Okay, so we are still in Chapter 7, Section 6. We are still discussing centers of mass and moments. Only now we're going to try to find the center of mass of some more interesting looking shapes, right? So this is going to be our first example. You can imagine that this particular object you would like to be able to find the center of mass of. Now, in this case, we are, we refer to these as finding the moments and center of mass of what we call planar laminas, right? Now, there's some things that we're going to assume, right? So I'm going to give you some formulas for finding the center of mass, etc. But there's some assumptions that we're going to need to assume, right? And they're not very realistic assumptions. So for example, whatever object this is that we're trying to balance on this pencil, we need to assume that the density is uniform throughout the entire object, right? Like this side over here can't be heavier, denser than this side over here, or this point over here. Like it has to have the same density throughout the entirety of the object, right? So this idea of uniform density. Now, I agree with you that the majority of the objects in our 3D world are not uniformly dense. But the ideas that you're going to learn here are going to be refined if you happen to take me for Calc 3. And we're going to use the same ideas, but then we will deal with that uniform density idea, okay? So let's start. I mean, look, the mass is just density times area. Let's think of it like that, okay? So what am I trying to address right now? So notice that, let's see here. Did they give the mass equation in that? Here, let me, I don't know. Yes, they do. It's right at the bottom. I'm sorry. So mass, and I'm going to try to unpack this. So if you're dealing with these planar laminas and you want to find the total mass of that system, it appears that we're going to be integrating, right, over some interval of f of x minus g of x with respect to x. And then it appears that out front here that looks like a p, but that's actually a lowercase Greek letter rho. If I'll probably end up calling it a p for the majority of this class, but nevertheless, hold on. Before I do anything, how do we go from here to here? This is not that bad. If mass is equal to density times area, well, let's think about that for just a quick second. That's density. And how can we write area? Well, area is just what? It's just length times width, or in our case, we'll call it height times width. Right? That's area. And if we look at this picture here, if you wanted to find the height, right? If you were trying to figure out the height, well, that would just be the top function minus the bottom function, right? So that's how we can go. First off, this rho is what we use for density. So where does that rho come from? That is what represents density in that problem. And then, of course, if you want height, it's just f of x minus g of x. So that would give you the height at any point. And then the terminology we've been using for width has been delta x, or dx is what we've been using. So you can see how we can start to piece together this integration formula for mass, right? You can see that where the dx comes from. This is literally just density, and then we have times height times width. We're only interested in the height from A to B, right? We don't care about what happens over here. So that's why you can think about, if you integrate from A to B, that would give us this whole area, and that is exactly what we multiply by density to get mass. Okay, so no more theory up front. Let's just do a problem. So what is our job? So our job is to find the center of mass of the following lamina of uniform density, rho, bounded by the graph of 4 minus x squared and bounded by the x-axis. So here's your x-axis, right? So you're bounded here. Does not go past the x-axis. And then you're also bounded by the graph of 4 minus x squared. Okay, so I agree with you that 4 minus x squared continues this way, but because you're bounded by this x-axis, it's not going to let it go any farther. Okay. All right, so this is your overall shape. Every point in this shape has some x coordinate and some y coordinate. Agreed? So this is our equation. All right, I agree that we could cheat. We already got the center of mass, so maybe we, but so what do? Just skip it, go to the next problem? Well, let me show you, because the real goal is to make sure you can get to that answer. So let me go ahead and get started. So when all is said and done, this is what we should write as an answer. Okay? So this is what we need. We'll put some x bar and some y bar here. I want you to spot. Let me show you a trick that you can use to save you some time. So notice that any parabola has a certain symmetry to it, right? I mean, you could fold that parabola across that dotted line and it would line up perfectly, right? So because of that symmetry, we know that when you're trying to balance this shape here, we know that this center of mass is going to be somewhere on this y-axis, right? That's just due to the symmetry of the parabola. The center of mass is going to be somewhere on this y-axis. Now, what do we know about any point on the y-axis, right? Any point on the y-axis has an x value of 0. So notice how I'm going to go ahead and jump right here and say x bar is equal to 0. I didn't have to do any calculus to figure that out. That's just due to symmetry. The rest, we need to be able to do the math and show the work. So the only thing we need is y bar, right? The only thing we need is that moment. So to get it, we're going to need the mass of the system. That's where we're going to start. And we're also going to need the moment about the x-axis. Let's start with the mass of the system. So the formula that we're going to use, so mass is equal to, honestly, you can leave this row out of this because it's going to cancel out in the end anyway. But because eventually you're going to need, in Calc 3, you're going to have to know the density. So I'm just going to leave it for now. So let's go ahead and calculate the mass. So that's just going to be, well, notice that we're on the x-axis, we are bounded from -2 to +2. So that alone is what's going to set up our bounds from -2 to +2. And what is it that we're actually integrating? Well, we're just integrating the function 4 minus x squared with respect to x. So this is an easy integral. So that's just 4x minus x cubed over 3, -2 to 2. And so what do we get for the mass? We get a mass of 32 rho over 3. Okay, so after you do your f of 2 minus f of -2, the result of this is right here. Okay, so we now know what we'll be subbing in for m, but we still don't know what to sub in for m sub x. Okay, so we're going to be using the following formula. Well, what is g of x in this case? Well, clearly f of x is 4 minus x squared. But what is g of x? Well, don't you remember we were bounded by the x-axis? So the other function is the x-axis. So g of x just equals 0. Y equals 0, you can think of it. Okay, so that's good. So we plug in a 0 here for g of x, plug in a 0 here for g of x, and we're going to be subbing in 4 minus x squared here and here. Ready? Let me go ahead and set this up. So rho, we're going to be integrating still from -2 to 2. And now it's going to be 4 minus x squared over 2 times 4 minus x squared dx. Are you with me? Plug 4 minus x squared for f here and here. Plug 0 in for g here and here. All right. So let's just simplify this. I'm just going to FOIL it out is what I'm going to do. I'm going to, this dividing by 2, that's the same thing as 1/2 times. So I'm going to bring that 1/2 out front. So, you know, p or rho times 1/2 is just rho over 2. Still integrating from -2 to 2. And if you will allow me, I'm just pretend like what's left after I bring that 2 out, this, I just FOIL that. Okay, let me get you to the result. That would just be 16 minus 8x squared plus x to the 4th. Okay, so now we simplified enough to where we can integrate. Let me get rid of that integral. So now I'm just going to go through and integrate. So integrate 16 with respect to x, you get 16x. 8x cubed over 3. X to the 5th over 5. -2 to 2. All right, so at this stage, it's just f of 2 minus f of negative 2. We're just plugging in a 2 for x minus plugging in a negative 2 for x. And the result of all of that is 256 rho over 15. Okay. So I should, well, I'm just going to free up some space by erasing this formula here. And then I'm going to go ahead and finish this problem up. That will conclude this this section. I mean, you want to practice, obviously. I mean, this is a fairly easy one, but it gets the point across. So let's go ahead and plug m. So that's 32 rho over 3. And then let's plug in for the moment about the x, which is 256 rho over 15. Okay. So this is going to equal 8/5. The rows, as I said at the onset, cancel out, right? I mean, look, that's 256 rho over 15 divided by 32 rho over 3. What do you do when you divide fractions? You flip them and you multiply them. When you flip this, you'll have a row on the top and bottom, and that's why they cancel. Okay, so if you at the location 0, 8/5 is where you could balance this lamina. That'll be it. Take care. I'll see you in the next videos.